speak on this, then you can connect the dots, okay, with what I was talking about. But as a reference, first let me mention, you can see Rudin, the first, the basic baby Rudin. Yeah, what is it called? Real analysis. Yeah, just principles of real analysis. Okay, principles. Yeah, this is the only one that has principles. So yeah, because, and this is chapter 9. Okay, chapter 9, but obviously not the whole chapter. You don't need. Chapter 9, functions of several variables. Read the first section. Okay, they introduce linear transformations and norms on
It's
linear.
principle of mathematical analysis,
Principles of mathematical
I
analysis.
guess.
Yes, yes. So not real analysis. Principles of mathematical analysis. Right. The next version is real and complex, and the next one is for functional. And the functional one is really where they do all this for infinite dimensional function. That is very interesting. But stick to this now, and it will be soon. You will go there. Yeah. So this is the reference. So that's fine. But let me just talk about it in a way that you can just use all this nicely. So let me call this norms on matrices. Let me not use the word linear transformations. Okay, let me just say norms on matrices because we are doing matrices. And in fact, even in RTIN, I saw that if you do the problems, which is at the end, right? Additional problems are there, right? There you will use or need all this. Okay. In the main exercises, as you say, he sticks to nilpotent where it just ends at a point. So you don't need to go to infinite case. But in reality, you will have to go. So norms on matrices. So let us fix. So let's do it in general. Okay, let's not do it for 3 by 3 or anything. We are mathematicians. Let's do it in general. But let's keep this R and call it C also. But fine. So A is a n by n matrix. Okay, we want a norm on A. So there is one norm on A, which is the very simple norm. I will only talk about two norms. Okay, there are infinitely many norms. First thing, but most of the norms, all the norms are equivalent. Fantastic thing. But we will not talk about say all that. Okay. One norm is something which you all of you know, which is just that you view this as a vector in R to the n square, right? And then just take the right here. I should put square root because I don't know what is going on. And you do this, then all your Cauchy-Schwarz, Minkowski, Holder's inequality, all the Olympiad stuff which you have studied earlier, so it all comes into play. In the correct setting, this is the setting for why those inequalities are fundamental. They are easy, but they are fundamental. But this is just over entries. Okay. This norm is nothing new. Already know it. Okay. There is another norm which is very important. Okay. And that norm I have to introduce. That norm is very important because this norm doesn't have some properties. Okay? But what properties does it have? Nothing will be surprising here, but you should check it. Please check these things. Okay. This is 0 if and only if A is equal to 0. This is easy. But these things you must check. Otherwise, you will not know if these are true. You will just be assuming it. And then you will say it to be true in places where it is not true. So that should not happen, right? So this is less than. So I'm putting 2 here, you understand, because it's a square root and it's a usual business.
So is it somehow related to like setting up metric spaces? I don't know, setting up the actions when we.
Yes,
okay.
it is related to that. And
normed spaces, something like that.
Sorry?
Normed spaces.
Normed, yes, exactly. Yeah, exactly. But we are only looking
Yes,
at one
the
matrix.
same the same metric spaces playlist. He proved the axioms. He proved
Yes.
that this satisfies.
Right, exactly. These things are a bit more than metric spaces, but they are Hilbert spaces. They have the notion of angle also, in some sense. But because you have Cauchy-Schwarz, that metric spaces don't
inner
have.
product.
Yeah, they have an inner product. Right. But let's not
Yeah.
think of it in so nice general setting now, because we want to just prove this with hand, bare and basic. Okay, that is important for us. But yeah, it's correct. This thing, and obviously some very easy stuff, but I should write it. This lambda is a real number. Am I missing anything? Fine, it's okay. Yeah. So these are the properties it has. But I will introduce one more norm, and focus on this very carefully. We will not put any subscript here because this is the norm that actually is studied all the time. This norm is not so good in some sense. Not so convenient. Yeah, that's the only thing. So the norm I'm going to talk about is specifically suited to things that have a multiplication as well. Matrices end up having a multiplication also, right? But vectors don't have multiplication. So anyways, this norm you should see. This will be supremum. This is the usual norm. This will come in Rn, right? Ax is in Rn, everybody, fine? And you just take the usual norm in Rn. Okay, so you take the supremum over, so you take all vectors of norm 1 in Rn, evaluate, and collect them, collect all the values and take the supremum. Okay, this is not nothing strange. Okay, this is just preparing for the worst, right? Kind of, right? You take all the vectors and you take all the outputs and you take the supremum of those outputs. Not a bad thing, right? So this is a show that this is also a norm. That is a good homework. That is something which you should do, right? All this is shown in Rudin, but you should do it because
Can
these
you,
are
can you please explain again, like what a supremum of like A? I
yeah.
didn't
So
quite
we'll
like.
do it. We'll do an example. Just do an example. So let's say that it is like this. Okay. So you will want to have the norm of this, right? So what will you do?
Okay.
You just take 1, 0, 2, 3 and evaluate it at all the vectors. Norm is equal to 1, right? So yeah, just x1, x2. Okay. And then you take the usual norm and you are doing this over all the vectors for which this is equal to 1, right? This set, take the supremum of this set. What's wrong with this? Right?
Okay.
And you can calculate it. I don't think I'll do a good job in calculating things, but you should just calculate it. Because this will be just a very simple thing. It's just some x1, you can do it better than me. 3x2. And then this norm, iska norm is what? Iska norm is, but we never do it like this. Don't worry that it is such a clumsy thing. Okay, we'll never calculate the norm explicitly. That we don't do in mathematics. Usually, I mean, of course we do, but usually that will not be the prime. The problem will never ask you to do that. And if it asks you, then it will follow from something theoretical. And you do. I mean, this is just a number, so it's just a square. And you have to find the overall exponential.
This is a norm that we defined. Okay, so you're telling like computer such norms and take the upper bound of it.
Yeah. Over all the things and take the upper bound. So it becomes an Olympiad inequality, right? Find the maximum of this, or just calculus in two variables. Find the maximum of this,
Right.
x1 square plus. But you'll never need to find it. Okay, that is usually not will be asked, not asked. Okay, so this thing. But what we are interested in is prove 1, 2, and 3. Prove 1, 2, and 3. That's the homework.
Right.
You should do that.
So 1 and 3, I guess, is easy.
Yeah,
it's always
easy.
triangle inequality.
Which is also easy, but you should do it, right? And the next thing which you should prove is this, which is actually the interesting thing.
Triangular inequality. I mean, second one, I guess.
Yeah, but the third one is submultiplicativity. Name is not, but you can understand. This is what is the key thing. You should prove this. Okay. Prove this. And then prove, this is another amazing fact. Find a number C1 and a number C2. And these are actually easy to find. Nothing. Show that there exists such C1 and C2. I will show you how to find one of them greater than 0 such that 4 holds. Oh, this is the key, very, very important thing. So these two norms are connected. These two norms are related, not out of the blue. Okay. So the second one is a norm because it satisfies the first three things. It's a nice norm because it satisfies that extra submultiplicativity. And it is related to this norm because it is related. Okay. We will find C1 and C2. You have to find C1 and C2. You don't have to find the best C1 and C2. Maybe I think you can find that. But we have to find C1 and C2. Let's try to find C1. I'm just anyone, right? So let's try to find C1. But do you understand what I'm saying? So you take any A, right? And this will be true for all A. Yeah, sorry about that. I did not say that actually. So that one C1 will work for all A. Okay. Any A you take this norm and you take that norm, there will be a scaling. You can scale it by C1 so that the second norm becomes bigger, and also there is a C2. So they hold each other accountable in a way. Very, very important. Okay. Let's do this number 5 right now. Okay. Some nice mathematics. And this also actually follows from continuity and compactness, but we will not do that right now. We will do it with bare hands because matrices are very nice concrete objects. So we have to find this C1. I think for one of them, I remember you need Cauchy-Schwarz, and the other one is just you do it with just, I suppose, triangle inequality. I'll do only one, and we'll do one, and the other one will be home. So let's try to do this one, right? Right. Yeah. So, and this you want to show for all A. Okay. For all A. Hmm. Let's take, because I have not prepared this. I know some root n or something works, but okay. So let us, this norm, we can write this nicely. Means write it in a way. First column, and then you second column. There would be better way, but yeah, let's. When you write it, you will see that it's actually a very concrete question. Okay. You want to show that there is a C1, not just show there is a C1. That is not difficult, but you want to find a C1 such that this is less than this. And what is that? That is the maximum you can get over norm 1 matrix. So, so you take AX right? And you want to say this is less than, and finally arrive at this sum of squares. So yeah, I just some Cauchy-Schwarz. So this is equal to, eventually you don't want to write. So this will be equal to A1I. It's been 3 years at least since I did this calculation, because we never you never usually use the exact bounds. But it's time to do it. So this is the first vector, sorry, first coordinate. Second coordinate is, just check me, okay, after multiplying.
Right.
I'm not writing the indexing, you understand. I goes from 1 to 1. And then obviously you take the norm of this, right? Take the norm of this. So you take the norm of this, right? And then you have a sum of squares, right? So you see that would be, no, sorry. Nonsense. Yeah, I get it. Yeah. So let me write it. Maybe I could have directly written it. So I'm just writing it, okay? So you see, you can see that this is going towards Cauchy-Schwarz. Right? This is square. Because you want to separate the xi's, right? You want to remove the xi's from all these things, right? You want to remove the xi's from all these things. That's your goal. And yeah, you can do it very, very crudely, but we will not do it very, very crudely. We'll do it slightly. Wait, I wrote this wrong. Yeah. We'll try to be slightly economical to give ourselves a chance to get a tight bound. Otherwise, it's not difficult, right? Yeah. Right. So start using Cauchy-Schwarz, right? So by Cauchy-Schwarz, what happens? Try to look at the first one and apply Cauchy-Schwarz, first summand and apply Cauchy-Schwarz. You know. Correct or not? First summand only.
Yes, sir.
Right? Yeah.
Yeah,
Okay.
Cauchy-Schwarz.
Yeah, just Cauchy-Schwarz. Obviously, because maybe you don't use Cauchy-Schwarz in the correct way, means that not correct, I should say. It is stated in a clumsy way, and maybe that's why. But and this is also I'm using it in the clumsy way. Otherwise, it's a very nice way to talk about it. But for that, one has to get comfortable with norms in inner products. Then Cauchy-Schwarz becomes a very elegant inequality. But yeah, you can't develop all the elegance in one day. So it is like this. Okay. So yeah, now I just write it in a different place. But you can see it's coming, right? Okay, it already came, right? Already came, right? Yeah. Summation a square. Summation. Oh wow, I feel good. Right? Square. This thing, and also there is this thing which is norm x. Okay? Norm x. This is just norm x, right? Yeah. This is just equal to it. Any problem?
No, sir. No problem.
Yeah, Arnav, is it okay?
Yes, sir. Okay.
I'm just, yeah, Just doing the easy stuff, right? Just taking it and saying this less than this, less than this, less than this. At one point, I've only applied Cauchy-Schwarz. Okay, and so you know that actually equality can hold because it's Cauchy-Schwarz. So you know equality can hold for appropriate matrix A and for appropriate vector X. Okay, right. And so, so what should we take as C1? Just 1, because this is less than 1. Okay. So finally, if I write this in a green box here, orange, what did we get? We said that we got that this AX is less than this A2 norm, right? This is the A2 norm, right? Is less than the A2 norm times norm X, right? Which is norm X is maybe equal to 1 actually, right? So just simple fact. And so you can take the supremum, right? It will still remain less, right? Take the supremum on both sides. It is right side, there is no supremum actually, right? So this will just become norm A is less than this. So it's actually less than that. The C1 is actually 1. Please do this again on your own maybe. Okay? And do the other direction, right? You see, we did not assume anything about the matrix A and did not assume anything about X beyond the fact that norm X is equal to 1, which was just the definition. Okay, so this is 1, but check it again. And this direction you have to find. This is probably the root n thing. Yeah. But that's it. Okay. Now we will show how to use all this matrix. Ready? Right. So we have developed actually the required thing that you need to know for norms on matrices. These are some important things. Yeah, now we'll just finish that problem. So in that problem, what was the thing? Problem was that A is a matrix, and let's n by n, doesn't matter now. We'll just write n, it means n by n, and what was given to us was that this norm, what that condition, that complicated looking condition was just saying that this norm is less than 1. Okay, let's keep it easy like this and say that this norm is less than 1. This norm is this norm which we just talked about. It's a norm you have to check, but after you've done all that, okay, this norm is less than 1. And the problem was to show that I plus A is invertible. In fact, much more can be said, but I plus A is invertible. So you had to look at this quantity, right? This infinite quantity. And then what did we say? We said that, we said that, let me write it more words. For any epsilon greater than 0, there exists a k, maybe there exists a n naught, such that for all k and s bigger than n naught, bigger than equal to n naught, what did we say? We said that a to the power k s, this with respect to this norm, remember we were able to show for this norm because this is the nice norm with respect to this which you can work with the multiplication. Yeah, and I'm sorry, this is less than 1. Strictly less than 1 is 0, so we'll take half. You can take anything delta less than 1, but doesn't mind, take half. Okay. What did we show? We showed that this norm is less than epsilon. Do you agree? Why? Because it has triangle inequality, right? So this is less than norm a to the k minus norm. No, sorry, this will come, but not yet. This is just triangle inequality, k plus 1, just write it like this, right? And then the key thing is that submultiplicativity, right? The submultiplicativity will make it this. You agree, right? We get all these things.
Okay, so it just becomes
Yes,
the
just
normal real number.
it kind of becomes like, right, power of a normal power. Yeah, norm of power becomes less than power of the norm, right? And that's good. These are the facts. I mean, it's a nice thing that you have another norm which is more convenient, but that convenient norm is connected to that previous norm with respect to which you can show things. It's a in this going from one norm to the other is really the game changer. I mean, in fact, that so Arnav was, I think I was also there attending this thing in St. Xavier's, right, where they were doing all this. So they were like okay, like there's a disk and there's some strange motions, strange collection of motions, okay, which you can compose and still get still be in that strange collection. There were strange motions, but then they would introduce a new system, not a norm but a new metric with respect to which those motions will become linear motions. Okay, so you redefine your sense of lines, and then those complicated motions would become good motions with respect to that new distance. And then all the theory which you know for good motions, which is basically linear transformations, you can apply it. And that is sort of hyperbolic geometry. Okay, although obviously it's just a 6-day thing, but obviously that is slightly more advanced, but actually not. But yeah, I mean, it needs more training. But this is something like that. I mean, you change the norm and then it's useful. This, and then this is less than epsilon because, okay, so this. Let me erase this part. But how do you, but you need to go back to the Euclidean norm. Actually, you don't need to go back, but if you don't, then you have to do some more analysis and prove some more results. But this is less than epsilon, right? But then what do we know? We know that this implies that, so what can you say about the A2 norm, the 2 norm, the usual norm? Yeah. What can you say about the usual norm? That is less than root n, or maybe that's C2, right? 1 by C2 epsilon. Agree with me or not? If you go back and look at it, right? This comes into play. Okay.
So we have a constant such that this normal Euclidean norm is always less than that. So we can just translate it, and we've already bounded
the good norm. Yes.
The good norm.
Yeah, for us, and that's the thing. And so this means that this sequence is Cauchy sequence in R9. In Rn square, it's a Cauchy sequence with respect to everything that you know, Euclidean metric and everything. It's Cauchy, which means that term by term, every component is Cauchy, because that's how you will have to say, right? If a sequence is Cauchy, vector sequence of vectors, a sequence is a series of vectors, right? Cauchy, every term is Cauchy. Every term is Cauchy means every term is converging. So every term is converging, so it's going to converge to some matrix. Some matrix, and every term is a bounded real number because it's converging, because the terms are. You don't need to say all that because, but for that you have to come to some equivalence of norm. We are done. This is the thing. Okay, this is the thing. This is just the beginning, but yeah. So we generalize that result which was there in R10, which is for nilpotent. And obviously, I mean, if it's nilpotent, then I suppose you can show that the norm is, I don't know, what will be the norm for a nilpotent? No, actually, that's a different flavor. I should not jump. Yeah. The nilpotent matrix can actually have large norms. So that problem has its own merit, but it's much easier. It just happens for symbolic reasons. It just happens for formal symbolic reasons. But this doesn't happen for symbolic reasons. You have to go out of your arena of adding finitely many things and be okay with adding infinitely many things, which you learned first when you came to college, first year, or whenever. So maybe earlier these days. So that is the thing. Okay, that is the thing. Yeah. So unfortunately, we have learned these things, but unfortunately, we didn't solve those questions. But let's take one question at least from let's try. I mean, we shouldn't just leave it like that. Okay, we are ahead time, but let's do at least one question. So any suggestion, anything we should do from row reduction? Any one question, please? easy one we can do. Maybe.
Oh, from row reduction, I don't have, sir, but there was one under the miscellaneous problem section.
Okay,
Oh,
no, we will. Okay, we
I
will
didn't
not
get
go.
it.
Let's not go there today then. Okay, it gets a bit
Okay.
heavy. Yeah, so any Arnab, anything from row reduction, Rohan, anything from row reduction you want to do? Any doubts from row reduction? We can just take it a little bit now.
Yes, I have.
Yeah. Because now we should do something easy. But all those homework you should do.
Yeah, the question number 2.6 is too big. Is there any short way to do it?
2.6?
Yeah.
Okay, right. Right, 2.6. Yeah, there will be. It's some, I think it comes from inclusion exclusion principle, something like that. But yeah, one has to think about it. Yeah. But find its inverse. I don't know.
I mean, we can find determinant. So
But I think he doesn't
since
want
it's
to
a-
do that. Yeah, but I know determinant and adjective, but he doesn't want to do that, Arnav, right? Means that's very long actually. Determinant is very long.
So where will inclusion exclusion principle come?
Yes. So inclusion exclusion principle, I'll talk about it next day. It actually does.
Okay.
It is actually in the end claims the invertibility of some matrix. Okay, some combinatorial matrix and its inverse. But I'll talk about it. Actually, I don't.
I don't see it at all actually.
Yeah. But actually, that is what it does. It's a kind of inverse of some linear transformation between some vector space built with basis is built on sets. Like sets are its vectors, basis elements, and you do. But this one, yeah, that's and it's very
Yes.
nice theory, and which is even
Can I
third
ask
year
some-
people are doing research on that. Some BTech third year people are did some research based on that kind of thing in design, linear algebra and design theory. I'll talk about it next day surely, but maybe outside the formal this thing. But this one, let's come to this. Yeah. So what they want you to do in this problem. So first of all, it's invertible. That's clear. You see that. But yes, I got disconnected. Yes. Am I audible?
Yes, sir. Yes.
Yeah, I'm audible. Okay. Okay. Let me think. Yes. So you have to, what you can do here is use Gaussian elimination. Did you try that? I don't think we have.
Gaussian elimination means
Yes. Yeah. So you find the inverse using Gaussian elimination. Not, I'll try to do it the next day, but let me see. Yes.
I was just saying that.
Yes. Yes, go on.
I was just saying ki just implying the elementary row operations on the identity matrix and get it to the inverse.
Yes, that's what I'm saying.
I'm telling out that, but it's too big. And the 1, 2, 3, 4, 5, 5 plus 5 matrix.
Okay. Correct. It's too big. But at least, so you have this matrix, and this matrix. No. So you apply some, so this is, maybe we can be there only. Yeah. So, yeah. So you take the identity matrix. I'm just thinking for myself also. Take the identity matrix and you apply row operations on this and apply row operations on this analogous ones to the identity matrix also. And finally, when you make this the identity matrix, then this will become the inverse. Right.
So I think we can continuously row reduce and so.
Yes. Right. But he's saying that that's not very long. But I mean, if you call that long,
Yeah, like
then
subtract the second row and first with first row.
Yes,
Then-
that is fine. He sees that.
Right.
Yeah, the method. Yeah, I think you have to just use the fact that it's a Pascal triangle to apply the row reductions cleverly. The properties of Pascal triangle, because they add, right, things for second, third row, add to the whatever, those kind of, right? If you use those things, then it becomes faster, right? Yeah, that's one thing I can tell you. Yeah, apart from that, if you are asking general thing, yeah,
Will the inverse be also such a lower triangular matrix?
it will
I
be
don't
lower
know.
triangular, certainly, that you can prove. They have proved that inverse of lower triangular is lower triangular. They form a group. You can prove that as a homework. But if you are in general asking that if ith row and jth column is n choose I, yeah, and this matrix you find an inverse, yes, for this I have to talk about inclusion exclusion. Yeah, otherwise I don't know how I can say. Yeah. Yeah, maybe I can talk about that next day, and that will give us a easier solution. Apart from that, I can just tell you to do row reduction, and using the properties of Pascal triangle, row reduction becomes. So, for example, you add these rows and add to the third row, then the third row just vanishes, right? Or something.
Right.
No, maybe I'm wrong. Oh, sorry. No, how does it vanish? It doesn't vanish.
Like you can